Hi friends, today we discuss about the what is a capacitor and different types of capacitors. First, let's discuss about the capacitor. The capacitor is a component which has the ability or capacity to store energy in the form of an electrical charge, producing a potential difference across its plates. Capacitors are also known as electric condensers. A capacitor is a two-terminal electric component. It has the ability or capacity to store energy in the form of electric charge. Capacitors are usually designed to enhance and increase the effect of capacitance, where potential difference, often called voltage, is the difference in electric potential energy between two plates in a capacitor. A capacitor consists of two or more parallel conductive plates which are not connected or touching each other but are electrically separated either by air or by some form of a good insulating material such as waxed paper, mica, ceramic, plastic, or some form of a liquid gel. It means a capacitor is an electrical component that stores energy in the form of an electric field. It typically consists of two or more parallel conductive plates that are not physically connected or touching each other. These plates are electrically separated by an insulating material known as a dielectric, where dielectric means the plates are separated by a non-conductive material which prevents electrical current from flowing directly between them. Common dielectric materials include air, waxed paper, mica, ceramic, plastic, or gel-based substances. The purpose of the dielectric is to increase the capacitor's ability to store charge while preventing dielectric condition between the plates. The insulating layer between a capacitor plates is commonly called the dielectric. Due to this insulating layer, DC current cannot flow through the capacitor. In simple terms, the insulating material between a capacitor's plates is indeed called the dielectric. This insulating layer prevents direct current from flowing through the capacitor because it blocks the flow of electrons. When a capacitor is connected to a DC source, it charges up to the supply voltage, but the dielectric stops the continuous flow of current. The conductive metal plates of a capacitor can be either square, circular, or rectangular, or a cylindrical or spherical shape with the general shape, size and construction of a parallel plate capacitor depends on its application and voltage rating of the capacitor. The sentence explains that capacitors, which are used to store electrical energy, can have various shapes for their conductive metal plates, including square, circular, rectangular, cylindrical, or spherical. Square or rectangular plates often used common in standard parallel plate capacitors. Circular plates often used in disc capacitors or ceramic capacitors. Cylindrical configuration found in electrolytic capacitors where plates are rolled up like a jelly roll to save space. Spherical geometry found in rare but used in some theoretical models or specialized high voltage applications. The shape, size, and construction of a capacitor depends on its applications and voltage rating of the capacitor. The flow of electrons onto the plates is known as the capacitor's charging current, which continues to flow until the voltage across both plates is equal to the applied voltage Vc. At this point, the capacitor is said to be fully charged with electrons. The statement describes the charging process of a capacitor. When a voltage is applied across a capacitor's plates, electrons flow from one plate to the other, accumulating on one plate and depleting the other. This flow of electrons is the capacitor's charging current. The current continues until the voltage difference between the plates equals the applied voltage, at which point the capacitor is considered fully charged. The amount of potential difference present across the capacitor depends upon how much charge was deposited on the plates by the work being done by the source voltage and also by how much capacitance the capacitor has. The meaning in simple terms, the voltage or potential difference across a capacitor depends on two things, that is, the amount of electric charge stored on the capacitor's plates and the capacitance of the capacitor means how much charge it can be stored per volt. If you store more charge on the plates, the voltage across the capacitor increases. If the capacitance is larger, the same amount of charge will result in a smaller voltage. The source voltage, like a battery or power supply, does work to more charge onto the capacitor plates, creating the potential difference. By applying a voltage to a capacitor and measuring the charge on the plates, the ratio of the charge Q to the voltage V is its capacitance value of the capacitor. That is C, that equals to Q divided by V, where the equation C, that equals to Q by V, defines capacitance. It states that capacitance C is equals to the charge stored on a capacitor divided by the voltage across it. In simple terms, capacitance is a measure of how much charge a capacitor can store for a given voltage, where C means capacitance. This is the measure of a capacitor's ability to store charge. It's measured in farads, where Q means charge. This is the amount of electric charge stored on the capacitor, measured in coulombs, where V means voltage. This is the electrical potential difference across the capacitor's plates, measured in volts. The capacitance formula C equals to Q by V. This equation can be rearranged to give the quantity of charge on the plates. That is, Q equals to C into V. This formula tells you how much electric charge a capacitor stores when a certain voltage is applied. A larger capacitance means the capacitor can store more charge at the same voltage. A higher voltage means more charge is pushed onto the plates, where Q represent charge measured in coulombs. C represent capacitance measured in farads. V represents voltage measured in volts. Capacitance is the electrical property of a capacitor and is the measure of a capacitor's ability to store an electrical charge onto its two plates, with the unit of capacitance being the farad, named after the British physicist Michael Faraday. In simple terms, capacitance tells us how much charge a capacitor can store per volt of potential difference across its plates. The larger the capacitance, the more charge the capacitor can store for a given voltage. 1 farad means the capacitor can store 1 coulomb of charge with 1 volt across it. 1 farad is very large, so capacitors are usually measured in microfarad, means 10 power minus 6 farad. Nanofarads means 10 power minus 9 farad. Picofarads means 10 power minus 12 farad. The image depicts a simplified diagram of a parallel plate capacitor. It is a fundamental component in electrical circuits where conductive parallel plates. These are the two metal plates that form the core of the capacitor. They are separated by a small gap and store electrical charge. The positive terminal of the voltage source is connected to the plate labeled positive charge, while the negative terminal is connected to the plate labeled negative charge. Where dielectric means this is an insulating material placed between the conductive plates. It enhances the capacitor's ability to store charge and prevents direct electrical conduction between the plates. Where voltage source means this provides the electrical potential that charges the capacitor. The voltage is represented by the symbol V suffix C in the diagram. Where electrical charge Q means the capacitor stores electrical charge when connected to a voltage source. Positive charge accumulates on the plate and negative charge on the other. The image depicts the schematic symbol for a capacitor, a passive electronic component that stores electrical energy in an electric field. It consists of two conductive plates separated by an insulator known as a dielectric.